All right, welcome back, everyone. Today we'll talk about chapter number 3, which is on review of statistical inference. Now, some of the methods that you will see in this chapter might appear familiar to you. You might have taken some of these topics in your past courses. So the idea is to give you an idea, to acquaintance, to give you some idea about what type of statistical inference we're going to use in this course. All right, and then mostly, we'll mostly be concerned with 3 methods in this chapter: point estimation, confidence interval, and hypothesis testing. And to give you a little bit of background here, we talked about in chapter number 2 that we need statistical methods to model the variability in the data. And now in chapter number 3, we take it to the next step. Now we know how to model the variability in the data. And now let's talk about the quality characteristic, which usually follows some type of a probability distribution. And so whenever we collect some data, we're interested in identifying the probability distribution that the quality characteristic might follow. Not necessarily the probability distribution, but the parameters of the probability distribution. Think about sample mean, think about population mean, think about population variance, and things like that. Right, so let's take a quick introduction to these 3 methods, and then we'll dive into the details of each of them afterwards. All right, so beginning with a point estimation is nothing but a single numerical estimate of a population parameter. And then think about examples that you probably have done in the past. We use sample mean, which is X bar, which also called as sample average, can be used to estimate the population mean mu. So X is your sample mean and mu is your population mean. Similarly, we have used sample variance to estimate population variance sigma square. Now, many times when we compute these sample means, sample variances, they will have some variability because we're computing it from some data. And as the data changes, the estimates of sample mean and the sample variance might change. So it's, instead of giving a point estimate for a population parameter, many times it's useful to give a confidence interval so that we can capture the uncertainty in the estimate of that population parameter, right? So confidence interval then becomes, to define, it's basically an interval in which the population parameter lies with some probability. Now, even though I'm saying some probability, this probability is usually very high, something like 90% or 95%. So instead of saying some, you can actually call this as some very high probability. And then the last one is hypothesis testing. When we say hypothesis testing, we basically start by defining a hypothesis. So a hypothesis is a statement about a population parameter. So you make some statement about the population parameter, and then we use data to verify whether the hypothesis is true or not. Now, usually you write a hypothesis about the population parameter before observing the data, okay? And then you use data to, let me write it here, there's some issue here. So we say use data to verify the hypothesis. Okay, All right, so we'll start with point estimation and dig a little bit deeper. But before I go there, they're usually a well-defined set of methods for performing statistical inference. Now, you don't have to do all of these for this course. We are not going to collect data from a population in this course. But in general, when you encounter a statistical inference problem in real life, this is what you would do. You would collect some data from the population. You would compute some sample statistics from the sample data for the population parameter. Now, even in this course, we might not do number two all the time. In the assignments, I might ask you sometimes to compute mean, variance, but for the exams and otherwise, I would provide these sample statistics to you. So these sample statistics are basically X bar, which is the sample average, sample variance S square. You could have many other sample statistics, minimum of X, maximum of X, and then you can use minimum and maximum to compute range. All of these are statistics. And then define the distribution of the statistic. Again, we are not going to be doing this in this course. You're not going to be doing this in your assignment or your exams. There are a few places where we need the distribution of the statistics, but I will usually provide you the distribution of the statistic. And then the final step is making inference using hypothesis testing or developing confidence interval, which we will see in this chapter. All right, so we start with point estimate and some notations. So point estimate, as I defined earlier, it's a single numerical number as an estimate of the population parameter. And then the simplest example is your sample mean, which is X bar. This is equal to 1 over n summation of individual observations xi, I is equal to 1 to n. So this is basically 1 over n x1, x2, dot, 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 x plus xn. All right. Okay, so now we are going to use X bar to estimate population mean. So we use a specific type of notation here. We say that if we are going to estimate mu using X bar, the estimate of mu is written as mu hat, and mu hat is equal to X bar, right? So this thing right here is a notation for estimator, or let's just say estimate. That's better, right? Now, typically, and we're not concerned about this question in this course, but many a times we ask ourselves, what is a good point estimator? Because you could have multiple estimators. For instance, for sample variance, you can use sample variance to estimate the population variability. You can estimate standard deviation for population variability. You can also estimate range for population variability. And then the question is, which one of these are best to measure population variability, right? So to answer this question, we are not that much concerned again in this course, but to answer this question, you want to make sure that an estimator has a bias of 0 and has minimum variance. If there is an estimator for which bias is 0, in other words, is unbiased and has minimum variance, then that is usually a good estimator, or is a good point estimator, right? Now, I'm not going to go into the depths of this, but I want to quickly tell you what bias really is. Bias of X bar. So X bar is an estimator of mu, right? So let's compute the bias of X. Bias of X is basically expected value of X bar minus mu, right? So whatever we are trying to estimate is mu, and then E of X is the expectation of X bar. Now from chapter number 2, you already know that X bar follows a normal distribution with mean mu and variance sigma square over n. So if I were to compute expectation of X, I would get mu. We already have minus mu, that gives us 0. So X bar is an unbiased estimator, right? And so now if you want a general formula for bias, think about theta hat as an estimator or let's say let theta hat as an estimator of theta, then expected value of theta hat minus theta is your bias of theta hat, right? So we are not again going into the depths of the bias computations, but what I want you to remember is a good point estimator is always unbiased and has the minimum possible variance, right? Okay, now let's move on to interval estimation. Interval estimation, again, you have done this before. The idea of interval estimation is that if mu is the population parameter that we are trying to estimate, we say that the population parameter lies between an upper limit and a lower limit. And then the probability that mu lies in this interval is equal to 1 minus alpha, where alpha is your significance level. Significance level, right? Now, typically, if you're concerned with normal random variables, let's define the alpha as probability z greater than z alpha is equal to alpha. Z here is your standard normal random variable, and z alpha is just some number, okay? And what we're saying is that let's try this schematically here. What we're trying to say here is that if this is a probability distribution of a standard normal, so this is mean equals to 0, sigma equals to 1, we're saying that let's find out a z alpha such that, let's say this is your z alpha. We are saying that the probability that z is greater than z alpha, this probability is alpha, okay? And by defining this, now we can actually define our confidence interval. You can say that confidence interval for mu, population mean, mu is less than x bar plus z alpha over 2 sigma divided by square root of n, and it is greater than x bar minus z alpha over 2 sigma divided by square root of n. And then the probability that this holds is equal to 1 minus alpha. All right, and so this is your upper limit u, this is your lower limit. Okay, good. Now this alpha is usually given to you. You don't have to compute alpha, but you might need to compute z alpha over 2 given alpha, right? So z alpha is, without going into the derivation, we don't need to go into the derivation of how to compute this, but you can compute z alpha. This is equal to phi inverse of 1 minus alpha, right? And then phi inverse is nothing but INV norm on your calculator, and then you can plug in 1 minus alpha here. Okay. So if you have to compute, let's say, z alpha over 2, you would just, on your calculator, you can do INV norm 1 minus alpha over 2. That will give you the answer. Now, another thing you want to keep in mind is that what we just defined is a two-sided confidence interval. So this one that we just defined, this is a two-sided confidence interval. And you can also have one-sided confidence intervals, right? Let me give you the formula for that. One-sided confidence interval, one-sided. Here, you can have two possibilities. The first one is mu is less than upper confidence limit, which is equal to probability mu is less than x bar plus z alpha sigma divided by square root of n, and then the probability is equal to 1 minus alpha. And you can have a lower limit. You can say mu is greater than L. This is equal to probability mu is greater than x bar minus z alpha sigma over square root of n. This is equal to 1 minus alpha. Right? This is your two-sided and the one-sided confidence interval. Let's take a problem and see how we can use the formula to solve a regular quality control problem. The question here is, the response time of a distributed computer system is an important quality characteristic. The system manager wants to estimate the mean response time to a specific type of a command. So we are interested in the mean response time of a specific type of a command. Let's write this down, mean response time to a specific type of a command. From past experience, he knows that the standard deviation of response time is 8 milliseconds. So we know some things about sigma. It's 8 milliseconds. If the command is executed 25 times and the response time for each trial is recorded, the sample average response time is 79.25 milliseconds. Okay, so it gives you the sample average response time, which is 79.25 milliseconds. And then it is also saying that you have collected 25 data points by executing this command 25 times. Compute a 95% two-sided confidence interval for the mean response. Okay, so two-sided would be upper limit is equal to x bar plus z alpha over 2 sigma divided by square root of n. X bar is 79.25 plus z alpha over 2. We need to compute this. Z alpha over 2, let's do maybe on the side. Z alpha over 2, this is equal to z of alpha is, you can actually see it from here, alpha is 5%. This is 1 minus alpha times 100%, right? So we can get alpha as 5% from here, or alpha equals to 0.05. So alpha over 2 is 0.025. And then you can do INV norm on your calculator, 1 minus 0.025, which is 0.975. And then this will give you 1.96. So let's plug it in, the formula. 1.96 times sigma is 8 divided by square root of 25 is 5. That will give you an upper confidence equals to 82.386. And then similarly, you can compute the lower bound, which is x bar minus z alpha over 2 sigma over square root of, and everything remains same except for that minus sign, and then you get 76.114, right? So that is your upper limit and then the lower limit. I'm also asking you to compute the lower confidence interval for the mean response time, and why don't you try this your own and see if you're able to get the lower confidence interval on the mean response time. All right, fantastic. Okay, next we'll move on to hypothesis testing. Now, I already gave some definitions of hypothesis testing already before, but let's try to revisit hypothesis testing. Hypothesis testing, let's start with the hypothesis. A statistical hypothesis is a statement about the values of the parameters of a probability distribution. Null hypothesis and alternate hypothesis. Now, whenever you perform hypothesis testing, you have to set up your null hypothesis and the alternate hypothesis. Now, null hypothesis is usually something that you assume to be true when you have not observed the data. Okay, something that rationally makes sense. Think about it this way. So let's say you go to a city and you want to dine out for dinner. And so you look around the restaurants and then you see a restaurant which looks nice and fine and everything is good. Now, there's no reason for you to believe that that restaurant is going to be bad. right? So if you are setting up a hypothesis here, you would say that the null hypothesis is that the restaurant is good. And so the alternate hypothesis becomes now that the restaurant is not good. And now you want to go back and collect some data. So you want to maybe go to Yelp or Google reviews and look at the reviews. And now based on the reviews, you can test whether your hypothesis was true or not. Okay. Now, when you do hypothesis testing, you only test the null hypothesis, right? And then you only either reject or fail to reject the null hypothesis. Now let's talk about why we do reject and fail to reject the null hypothesis. Why can't we accept the null hypothesis? The reason that we cannot accept a null hypothesis is that your inference is based on some amount of data. Now keep in mind, as you get more data, your inference might change, right? And in hypothesis testing, you're always trying to somehow reject the null hypothesis. All right. So if you get some data, based on the data, you can either reject the null hypothesis, or if your data is not strong enough, it doesn't give you enough information, then you fail to reject the null hypothesis. And a simple example to reaffirm this thought is, think about when a defendant goes to a court. The judge in the court usually can say that the defendant is guilty or not guilty. The judge never says that the defendant is innocent. It is because the prosecution can always come up with additional data, more data, to prove that the defendant is indeed guilty. Right? Failing to show that the defendant is guilty is basically not guilty. So I hope that gives a little bit of idea about why we say we can reject or fail to reject. We never accept the null hypothesis because we can always collect more data, and we can reject the null hypothesis. All right, so whenever we do hypothesis testing, reject or fail to reject, at some point in time, there is a possibility that we might be making some mistakes. Because keep in mind, again, every conclusion that we are making is coming from the data. So if the data is not good, if the data is not representative of what is happening, then you might end up making a wrong inference, right? And that leads to two kinds of errors. So I'm going to spend some time on this and try to explain what these two kinds of errors are. And I'm going to take a simple example where I'm going to assume H naught is defendant in a courtroom is not guilty. Think about it this way. If there is a defendant in the courtroom, and if you do not have any evidence, then there's no reason for you to believe that that person is guilty, right? Rationally, you would want to say that that person is not guilty. Now, our objective, or the prosecution's objective, is to collect as much data as possible and prove that the defendant is guilty, right? And if the prosecution is not able to collect enough data, then they basically fail to show that the defendant is guilty. And so we say that person is not guilty. All right, so with this example, let's start by defining type 1 error. Type 1 error is, the definition is null is true. Still, we reject the null. Reject null. And then the probability of this happening is known as type 1 error, or alpha. Let's look at an example. Let's say the defendant is indeed, defendant is not guilty, but the jury decides, for some reason, let's say the jury decides that the defendant is guilty. right? So the defendant is originally not guilty, but for some reason, somehow, because of some evidence, the jury decides that the defendant is guilty, and this leads to type 1 error. In the quality control context, think of the example where I am a manufacturer. Let's say I manufacture certain parts and my parts are good. So let's say part is good, but it was still rejected by a customer. So part is rejected. Probability of this happening is type 1 error, right? So in some ways, this is also known as false positive rate, because even though the part is good, we are saying that the part is bad, or we are rejecting the part, right? We are saying it's leading to a false positive. And I'll come to false positives and false negatives a little bit later, but right now, let's just try to understand type 1 and type 2 errors. Now, beta, on the other hand, this is equal to null is not true, but we fail to reject null, fail to reject null. Probability of this happening is your type 2 error. Now let's look at the two examples that we are talking about. Let me create some space here. Okay, so the defendant example, let's say the defendant is in fact guilty. Null is not true, right? Let's say the defendant is guilty and still the jury decides that the defendant is not guilty. And this is possible, right? Let's say for some reason the jury could not find enough evidence against the defendant, and then decided that the defendant is not guilty. The probability of this happening is your type 2 error, is known as the type 2 error. In the quality control context, let's say your part or my part that I was making, part is indeed defective. Part was defective, but the part is accepted by the customer. And that is your type 2 error. Right? And in many contexts, type 2 error is also known as missed detection rate. And in this case, think about it this way: the part is faulty, but still it was not detected by the customer, and then the customer accepted it. So we call it missed detection rate. So this is missed detection rate, and then alpha, type 1 error, is your false positive rate. False positive rate. Okay. Now, there's a nice little way in which you can organize your type 1 and type 2 errors. And I'm going to use an example here, slightly different example maybe. It's not different, actually, it's a similar one. Let's say in quality control context, H0 is part not faulty. Let's use this example. And you can organize type 1 and type 2 errors in this table. The first column of this table is H, alternate hypothesis, HA. For this example, HA is part faulty and H0 is not faulty. That's your hypothesis. And when you collect some data, now you can make some inference, right? So along this axis, you have your inference. You can either infer that the part is faulty, or you can infer that the part is not faulty. Okay, now if you go back to the definition, if the part is not faulty, in other words, if H naught is true and your inference is that it is faulty, then it leads to type 1 error, alpha. The second scenario was if H naught is not true, in other words, HA is true. So in this case, you would say that the part is faulty, but your inference is that the part is not faulty. That leads to type 2 error, or beta. Now there are two more boxes. If the part is indeed not faulty, and then your inference is also not faulty, then that's called confidence. And then this is 1 minus alpha. And on the other hand, if the part is really faulty, and then you are also able to infer that the part is faulty, that's called power of test, which is 1 minus beta. Again, power of test is a very useful measure for doing lots of statistical hypothesis testing. And then this table right here is surprisingly called a confusion matrix. Surprisingly, or maybe not so surprisingly, it's called a confusion matrix. All right, so let's see if we can do a little bit of hypothesis testing. And there is a very important concept associated to hypothesis testing, which is p-value. So we'll talk about these two a little bit when we return for our next lecture. All right, thank you. Subject.